Um, I'm Dennis Docter. I am a developer at Spil games. First question, any of you ever had to deal with like spaghetti code or, lots of... So I'm gonna talk today a little bit about our adventure to turn our big bowl of spaghetti into some nicely structured and layered lasagna. So first, a little bit about Spil games and where we come from. Spil games is basically mainly a publisher of online casual games. We host about 50 portals worldwide, localized and targeted to specific audiences like girls and family and teens. We draw about 200 million unique users per month with various types of games, mostly casual games, social games, but also games on your tablets and cell phone devices. We've had a nice and steady growth over the past 5-6 years, from less than like 15 million to the numbers we are currently at. And obviously this takes quite a bit of work to support, so the tech department grew exponentially to support this. And we brought in a lot of contractors, external companies to help us, lots of leavers, joiners, and lots of these people, we didn't really have the time to put the heads in the same direction, so everybody just, did their own thing and contributed to our spaghetti bowl, which led to our current system design, which looks a little bit like this. Lots of stuff going all over the place, interfacing mixed with business logic, caching in various levels, database schemas all over the place, and as things grow, your databases grow, and at a certain point it just doesn't scale anymore. So we try to alleviate the problem by doing things like making multiple reader databases, but obviously writer database bottlenecks remained. We had all our components talking to each other, and since everybody had his own cache, you were hitting several cache layers at once, and they were not always in sync, so it's really hard to predict if a user would get the correct data. So, to sum it up, we had like a big inconsistent design. The interfaces, each of the components had their own set of interface patterns. It was not really clear where everything was, and we accumulated quite a bit of technical debt. So it was like swimming in the mud. But it was not all bad. We earned a lot of money with it. So here we are now. We have a very nice view. But it's a precarious balance, and we climbed up there ourselves. So yeah, time to do something about that. So what do you do when you start fresh? First thing you do is come up with some fancy words. Our new architecture was to be flexible, predictable, and scalable. So what do we mean by these words? That obviously the explanation came after coming up with the words. So flexible, we need to be able to change where we need to change without having to, stick things together with duct tape. We need to be able to service all the different clients to our system as they need, and not as the service or software component thinks is designed. We need to be able to, think of something today and implement it tomorrow, basically. And another thing, currently we run on our own hardware, but we want to be able to deploy this to any kind of hardware, virtual machines, cloud systems, you name it. Predictability, very important. We need to be able to know what will happen when we do a release. We need to be able to predict the behavior of the system, and we need to be able to have like a really stable API, so client software connecting to our system knows what to expect and knows how to implement. And we need to be able, need to have predictable response times. And last but not least, predictable delivery times. Like we need to be able to know how long it will take to develop a new feature or product. And scalability, I don't think that really requires an explanation. So, these 3 points, they led us to make some choices. First thing is we want to make everything simple. Obvious one. Second thing, clean separation. So where first we had like stuff going all over the place. Now we want to create pieces which are responsible for one thing, and we actually can more easily predict stuff. We don't want dependencies horizontally. We want to have like a clear path through our system from top to bottom. And the last 2 bits, things must be able to keep running when things fail, and we want to be able to distribute over many machines. This led us to choose for a layered architecture. You know.
Can you do me a favor and take your lanyard off?
Sorry?
Against the microphone. Your lanyard.
Oh yeah, sure. So, yeah, layered architecture. This is your typical classic N-tier architecture, and we came up with 4 layers. From top to bottom, client layer, this is basically the stuff that connects to our system. We have various of those, like our portals themselves, stuff that runs in the browser, JavaScript, things like that. But also the games we run, they need to, drop their high scores, things like that. And the social games, they have backends, and those backends need to be able to connect to our system. So for these clients, we create client libraries to ease the integration to our system, but also it's not only for third parties, but also for ourselves. We have like a JavaScript library to ease our own portal integration. And these keep a little bit of state, the client state. So who is this user? Where is he coming from? What locale is he in? Stuff like that. Second layer, interface layer. Here we do the authentication. So authentication is not only username, password. This is like once a user has authenticated using his username, password, we give him some sort of a token, and that is kept at the client. So next time we can identify him. Here we do aggregation. So we pull data from the layer below, and we wrap this together, package it, and we can send this off to the client. We do no changing of data, just putting in bits and constructing output. Plus validation of input, really important. The service layer is where we stick the business logic. So what is business logic? It's like the authorization part. So, okay, we know this user, who the user is. What may this user do? May he see the last name or first name of another user? May he upload a high score? Things like that. Plus, it pulls the data from the storage and it can do some transformation on this data. So if we store an ID in the data for an avatar, in the service layer we can transform this to a URL. And at the bottom we have the storage layer, which is the only place where we do caching, for example. This is where we actually store the data. And it should take care of distributing the data for us. So at my application level, I shouldn't need to care about how this is stored or how big my data grows. This is handled down in the storage layer. And this brings us a nice bonus, having the caching done down there, plus keeping a little bit of the client state in the client, is that the middle two layers, we can keep them stateless. So this makes it very easy to scale up. So these are the basic layout of the parts of our system. Now the components of the system. How do we actually implement the stuff within these layers? We realized that we have within these different areas, we have hard problems and simple problems. Also, we have few very smart people, and it's very easy to come by more junior developer people. So we thought we should do something with that, and we thought of abstracting the stuff into two different building blocks. Firstly, which is the most common thing in our systems, just the regular application. These are very small and very simple to build. Anyone should be able to do this. They have little responsibility. They have, just a single thing to do. And this makes them easy to test and easy to deploy. Obviously, for the more complex stuff like the sharding and the processing of the stuff in our widget platform, which I come to later. These types of things, they're more difficult. So we actually created sort of platforms on top of which we could run these smaller applications. So we can abstract away the difficult things and have the senior developers work on this. These things are built to last. They don't have to be deployed that often. And the stuff that needs a lot of change remains small and simple, and we can deploy them separately. So, since we're a gaming company, I'm going to do a walkthrough, since we like cheating. So, from top to bottom, the client layer, I'm not really going to focus into it because this is actually sort of out of the application domain. It's at the client. We do not really have control over it. We create it, we give it out there, but actually it's not within. You can't really control what happens there, and you're not, you don't have to use our stuff to talk to our system. So at the top, the system of the interfaces. Take for example a social game or just a simple flash game, which talk to our system. The social game in this case is Family Barn. They want to get some user data for a particular player. So what they do, they do a HTTP post request with a JSON blob to our interface layer. This the data they send. It's not arbitrary. We have like a really well-defined API layer. The user interface, in this case, which takes the request, will then deconstruct the token, do the authentication bit, and see, okay, I know the ID of this particular user, and it will then start firing off requests in parallel to the service layer. So to get a user's profile, we need to fetch some different elements, like the data of the user himself. But for example, we want to have the number of awards this user has, the list of friends he has. So we fetch that data, we get it back, but the friends list is a list of IDs, so we need to enrich this with some user data. So we do another request to the user service after that to fetch the list of user data belonging to the friends, and then we can construct the output for the user's information and pass that back to the client. Key thing here is that the interface does as much in parallel as possible. For a high score, it's a much simpler thing. It will first fetch a list of high scores if the game wants to show a list of high scores, and then after that get the user information associated to each of these high scores. The other thing connecting to our system is obviously our portals. Here's one, and for this we build like a widget system. What is a widget? Well, if you look at a web page, it's composed of all kinds of blocks of functionality, really. And you could see these things as actually separate, calls to a separate interface on our system. So each widget is in essence the same as an interface. So what is a widget? For example, at the top we have the profile box, so we need to fetch some user data. The profile widget is basically a widget is basically a set of first a definition, and the definition is what is the input of this for this particular widget, a set of logic, to fetch the data, plus an HTML. Basically an early DTL template in our case, and these three combined result in an HTML output, plus some properties which can be passed back into the system. Come back to that later. obviously you're not requesting each and every widget separately. You're actually just, you know, fetching one page. So if you would look at the page, at the top we have like the header bit, and it's composed of a few blocks. So we group them into a header widget, which is actually a widget which says, okay, I have 4 child widgets, and these need to be created first, and then from their output I can create my output, and so on. So at the top I have like my homepage widget, which contains, which says, okay, I have 3 parts, a footer, a body, and a header. And they contain subparts, and everything needs to be you know, rendered in order to create this homepage. So in order to make this all work, these widgets, they are very simple. We do not want to have the logic in constructing all the stuff inside these widgets. We created like a platform to do this for us. So the platform, basically what it does is it provides all the HTTP transport. It's actually the host for the widgets, and it maps URLs to a particular widget. So if I would go to again.com, it would map it to the homepage widget, which which in turn has all these child widgets. So when you come onto the homepage, what the platform does, it will first construct a tree. So it walks through all these definitions, and it constructs a tree of all these widgets, and then starts executing the rendering step. Also, the platform takes any input parameters like cookies and post and get parameters, and it bundles them into a structure. It would do the authentication for all these widgets. So it actually creates a sort of context for each widget to run. And each widget has in its definition which parameters it needs. So the platform will actually only pass along the parameters which have been defined. So once it starts doing the rendering step, it will iterate over the tree and start rendering in parallel all these elements of the page. And you know, once one is done, once, for example, all these 4 ones below are done, then the one at the top can render, and so on. And then at the end, the page is rendered and is being returned to the client. So the whole widget thing sits at the interface layer. Obviously, there's some client code also being bundled here, but you know, these are JavaScript files, and they are not executed here. They are just delivered through here. So they're not part of the interface layer. So the profile widget in this case, it needs to show the username. So it fetches its data from the user service, and it fetches and it needs to display some score, which is calculated from the amount of awards. So it fetches some data from the award service. So what are these services? They sit below, and when a request comes in to fetch, for example, some user data, the context information is passed along, and the service then first checks the data, the context, So who is this user? What do you need? It fetches the data from the storage. Then, for example, if the user John has set his profile to private, then the user service will then filter out the stuff that the requesting user is not allowed to see, and then it can transform the avatar ID into a actual URL based on the configuration the service has gotten. So here we filter and we modify. We do not cache this stuff. Why not? Basically, we do not do very difficult logic. It's really just filtering and just small transforms. And you don't want to cache any like sort of poisoned data. So for one user, the filtering is different for another. So you would need to cache a lot of data, and the chances that you would hit the cache are very low. At the bottom, we have the storage platform. I'm not going to go into great detail on this. If you want to know more about that, then you either, if you have seen Enrique's talk yesterday morning, then you already know a lot about this, and otherwise check the video. Suffice it to say that it actually provides an API to our data. It's a sort of key value store, but with a schema. So we actually define the actual data that goes into it. So it's not just a key and a blob of data, but actually like an SQL table, we say what fields we have, and so we can do lots of cool things like filtering and sorting. But check the video. As a last component in our system, we decouple some data decouple some processes from the critical path, like sending emails or whatever. If a user registers, then they need to get welcome email. You don't want that to be handled in mainline. We did that before, and then the email system went down, and then the users could not register anymore. So that's not a good idea. So everything that's not critical to do, just decouple it. So what we did is we made a definition of the actual messages, which we could put on a message bus, and we use RabbitMQ for that. Which specifies what is the sender, which user are we talking about, a very strict schema of data to put in these messages, and each component in our system can put a message on it saying, hey, I did this. So we can create handlers to react to certain situations. So we're not actually sending messages to a particular process, but it's the other way around. If we want to implement some extra functionality, we can just hook into it and add this thing. These handlers, they should also be very simple, one task only. If we have 3 tasks to do on a particular message, create 3 handlers, so so we can easily trace what's going on. So after running through our system, we have all these components, and they need to talk to each other. And actually a quite tricky bit, because we run multiple servers, multiple versions. If you do a deployment, one version might not be the same as the other. When you introduce a new parameter somewhere, you don't want stuff to crash because the order of deployment was wrong or whatever. You just want it to work. So one thing was really important, that everything needs to speak the same language. And if I do a new deployment somewhere and I need some extra data, or I've removed some data, some parameter, it still needs to work, even if the middle component was not deployed yet or whatever. So yeah, we need some sort of messaging protocol which allows for, you know, skipping data which we get but we don't need, or allows for you know, still working if we don't get the data. So for this we use protocol buffers internally, which allows this behavior. And to the clients we could also use protocol buffers, but since we have like a lot of JavaScript-like clients, we also allow JSON there, which works very nicely. Obviously, that's not the whole story. If you are allowing these different messages, you still need to have like some sort of control over what happens. So we strictly define everything. Each input message, output message, each URL, each function, each type, the validation, everything is defined very strictly. When we do a change, we need to adhere to very strict rules. So if I add a parameter, it cannot be a parameter which must be there, because if I would do that and something has not implemented it yet, it would crash. So it must be optional unless you're very, very sure. Well, specification is all very nice, but you know, it must match the implementation. So in order to make sure that the implementation is the same as the specification, we actually generate the code. So the specification is the source for our basically our RPC code in all these layers. Also, the documentation is generated from this. So we can mitigate the chances of documentation being out of sync with what we have implemented. So how does that work? We came up with a sort of XML definition which allows of specifying all this stuff, but also it allows us to add documentation and things like that. Our system is, which we are building, is mainly built from Erlang components, but it doesn't have to be. So that's why we use this XML thing, because we can easily translate it into different kinds of outputs. For our Erlang systems, we translate it to Piki, which is a library which allows protobuf and JSON encoding and decoding, plus it gives an HTTP RPC interface. And it actually, from this Piki definition, we can generate the RPC and encoding and decoding stuff. So we ended up with like lots of small applications, and they run mostly on their own nodes. So we can deploy them separately, take them down. We can, you know, add where we need them. Many of them, they run on the same machine, and you know, when we grow our cluster, you know, we already have hundreds of nodes running. That gives a problem, because Erlang creates a fully connected graph. And we actually don't need that, because, you know, we only, from one thing, we only connect to just a few other things, and we know exactly which ones we want to connect to because of the definition. So we use hidden nodes. and that keeps the amount of connections nicely under control. So if I were to use just connect all the nodes in the cluster, it would explode. But in our case, we can have like loads of nodes without having loads of connections. This does need a little bit of administration. So we created a component which is a library we use in all our applications. Just our router library, our application really, which you feed a list of hosts, plus you feed a list of applications you need to talk to, and the router takes care of scanning all these hosts for nodes, and then scanning all these nodes for whether or not these applications are running, and then connecting to the nodes that runs something it needs. You can put a bunch of requests to this router, and it will try to send these messages, do the request in parallel to all the services or applications below. And this way, an application can only talk to the things you have actually defined. So you have a really clear path through your system. Response times. All these layers, there's lots of encoding, decoding going on, so that gives quite a, it could give some overhead, but we found that it's very, very low, typically less than a millisecond, but it does give us very predictable response times per layer, since they're, the things that are going on in each layer are really small, really simple. Everything is nicely detached. So for the price of just, adding this few milliseconds over the whole board, we get a really predictable response time, provided you have enough resources available. So. But it's easy to keep those available, since we can easily, scale up each individual bit. So how does this look like? This is what we currently see in our current PHP-like, Python-like environment. So the number of requests go up, and the response times nicely follow the number of requests. And this is what we're currently seeing in our new platform. Requests go up, response times stay the same. So that looks very promising. So some closing words. Where we are now, our interface layer, we have largely defined it. Most of it is implemented. We're implementing the service and storage layer. Obviously, we still have a lot of legacy going on, and we cannot do a big bang release. So we created Docter applications which allow us to use our new interface, and then at the service layer hook into our old architecture, so we can start using our new APIs. And then slowly migrate in the back. Within the next few months, we will be deploying two portals on the new Widget platform. Later this year, we are going to scale up to, we're currently running from one data center. We're going to scale up to multiple data centers in the second half of the year. Another thing is we're working on a system to do elastic deployments, which means I can define these are my resources. So I have a bunch of servers, and and I have a bunch of applications I want to run, and I can just throw them at them, and the system will figure out what to deploy where and how to connect everything. Get rid of our old architecture. And another thing we're working on is a new Erlang multiplayer game platform. Lessons we've learned. Well, the first one is sort of obvious, seeing the old picture and what we're doing now. It's very important that everybody has their head in the same direction when implementing stuff. We've tried to implement parts of our new architecture into our current portal deployments. Took half a year and it didn't work. So integrating stuff into something that's not good. Try to keep that. Try not to do that. Keeping layers with clear responsibilities really helps us in structuring and figuring out where to put logic. Strict communication is really important. Everything needs to be able to talk to each other. If it cannot talk, it will probably stop working. Small packages are really make for really easy deployments, easy testing. We change all the time. That's the only thing we always will be doing. And predictability is I think more important than any of the others. If you know what your system is doing, then then you can make changes to it. If you don't know what it's doing, it's really hard to do that. Any questions?
Yeah, on the router piece, is that something you guys like open source or something like that, or is it just totally internal and too specific to your app?
The way it is now, it is pretty specific. Yes. But it might be worth to investigate whether or not it can be generalized enough.
Right.
More questions about the router. Do you have like one per data center, one per node, one per layer?
Actually, each application has one.
Okay.
So in generally, there's one per node, because we run each application we run runs mainly on its own node.
Okay. And does every request go through the router, or does it, when it comes up, it gets a list of addresses from the router that it uses until it finds the address to be no good, and then gets more addresses?
Sorry, can you?
Does each request to other services go through the router?
Yes. Yeah.
You mentioned that removing the cache layers for improving, but in theory, it's supposed that the more cache layers you have, the better you at least reduce the latency.
Yeah, well, actually what we see currently, we have like many layers of cache, and we have quite a few examples where a failing cache actually gave us an improvement in performance. We really said, okay, the storage layer, it just needs to be fast enough. So there we do we make sure that data is properly segmented. So you don't have a really huge database which gets a lot of requests and gets really slow. You have like fast units, and they have a cache to make them really fast. And adding caches on top of that, it makes it less predictable and maybe save you a few milliseconds. But if if your average response time is like 30 or 20 milliseconds, usually your transport overhead is way larger. So we don't want to do that. Any more? Thank you.